Can you all hear me okay at the back? Yeah, great. Okay, so you've heard about Gaussian processes. What are non-Gaussian likelihoods? So where do we have observations that are not just Gaussian noise? So a very canonical example is classification, binary classification. Is the egg green or brown? But there's all kinds of other forms of that. So you can think, for example, of robust regression, so where you might have some kind of like some outlier corruption that's not just described by Gaussian noise. You could think of different kind of like data types, as Lisa was saying. For example, if you measure rainfall, you know it's going to be a positive number. You can't have -5 millimeters of rainfall. And also, like Lisa was saying, in like spatial statistics, we could have as an observation like a whole set of points. So then like a single observation is not just one number, a single observation is a set of, for example, locations where there was some disease cases. And in the following, I'm going to mostly focus on binary classification because it's maybe the easiest example to think of. So binary classification, we have some observations of class labels, 1 or 2 at different locations. How can we model this? Standard, kind of like machine learning 101 classification is logistic regression, but there's no linear classifier that can like separate these classes. So what we could do is we can move to like more complex models like support vector machines that give us nonlinear decision boundaries. And that's fine if all you care about is the decision boundary, but here we're talking a lot about Bayesian modeling. We'd like some distribution, posterior distribution over, for example, like what's the probability of being class 1 versus class 2, rather than saying like, oh, I'm 100% sure it's this class, even if it's kind of like halfway in the middle between the sets of observations. So what we could do with the Gaussian process is just pretend that it's regression after all, and we just have our labels be 1s and 0s for the 2 classes, and then just fit the GP as we've discussed like yesterday and this morning. And it's something you can do, but it has like some weird effects. For example, then your posterior prediction might go to values outside the range of 0 to 1. And what does it mean to predict that your probability for class 1 is -0.2? So what we would like to do is kind of have a consistent model that actually allows us to predict probabilities for the classes, for example. And sometimes it's easier to see things in 1D, so I've just got like another kind of toy example where we've got some observations of 2 classes, and if we just call them 0 and 1, and simply use a GP regression model, then the fit it kind of allows us to say like, okay, here it's probably class 0, here it's class 1, but it can go above 1, it can go below 0, so it just doesn't quite make sense. And so that's what I'm going to be talking about in the next hour and a half. So I'll very briefly like go back to the Gaussian likelihood to start with, and then we are going to look a bit more at what is the likelihood and how does it kind of connect the observations that we have in our data set with the Gaussian process prior that we use to kind of like model a distribution over functions with some functional properties. Then when we have non-Gaussian likelihoods, things aren't as easy anymore. It's not just nice linear algebra. Like what happens to the posterior over our function in that case? And it turns out that it's basically intractable. So then in the second part of this lecture, we're going to look at how can we approximate this intractable posterior with a non-Gaussian likelihood. And then finally look at kind of like a comparison of different approximations. And There are some maths on the slides, but like, don't worry if the maths goes over the top of your head. Like, it's basically impossible to like properly go through the details of all these methods in an hour and a half. This is more meant for you to kind of get an idea of like what's the language that we use, like what are terms, hopefully like some intuitive understanding of what they mean, and kind of like giving you a foundation for if you want to dig further into kind of like complex observation models, like, you know, how to start finding what you need. All right, so let's start with Gaussian processes with Gaussian likelihood. So GP is a distribution over functions. So here I've represented that with samples. So like commonly we just represent, like we just visualize a 1D GP with this kind of sausage plot with the mean and some confidence interval. But I think that's a bit misleading, and it's kind of like you really see more about the properties of the distribution that you're modeling if you just show kind of like a bunch of samples of them. And with the Gaussian process, all the marginals are Gaussian multivariate normal distributions, so they have a mean and a covariance, and we can look at the marginal distribution at some point and another point and their correlation. So hopefully that's all familiar to you now after the first four lectures. And nice thing about GPs is that we can just condition on an observation of our function and then get the posterior given, like in this case, one observation. And we can still look at the kind of like marginals and their covariances. And let's see, this works. Yes, so this is one of the visualizations that Lisa mentioned that I made, that you can kind of do the whole thing interactively and play around with it. I'll leave that to you for afterwards. So let's see if I get this away again. Oops. All right. So don't look at it now, you'll get distracted. But that's what we can do kind of like in closed form. We can condition on exact observations of our function. Now, the problem with that is if actually there's like a bit of noise in our data and you just want the Gaussian process to interpolate through all the data points, well, it's going to try its best, but that effectively means in practice that you get kind of like some overshooting as soon as you get away from the data points, because you're basically trying to fit something that's not smooth with something that's very smooth. So then how do we deal with this? We say like, oh, well, actually, we don't observe the function values directly because like we have finite precision sensors and measurements, or even just in our computer, we can only represent function values with finite precision, so there's always going to be like some error. And we model that with this kind of like error term, and we say instead of observing f of x directly, all we can see is f of x plus some error term epsilon. And then commonly we make this assumption that epsilon is IID, independently and identically distributed, zero mean Gaussian noise. And so you could write it in this kind of additive Gaussian noise form. We can also write it as a distribution over the observations given some function value f. So this is P of observation y given function value f. And that's the likelihood. And for Gaussian additive noise, the likelihood is just a normal distribution with mean being the function value, and then the variance is like your noise variance. And then that allows us to kind of like find the smooth signal that describes the mean, even though there's like a bit of noise around it. So this is great if your assumption matches the data, if you actually have just kind of like somewhat Gaussian distributed noise around the mean. If we have outliers, for example, then this would be a misspecified model. And if you have just two outliers here and you just do standard GP regression, then the single outlier here is going to drag the posterior distribution actually far away from the rest of your data points. And, well, you can't really fix this if you stick to Gaussian noise, but if you actually used a different observation model that properly accounts for heavy-tailed noise that, like, once in a while you have some larger outliers, then you can still get a regression fit that kind of gives you the signal that you're looking for. So kind of like how we define like what our observations are, like what properties are in the kind of process that goes from a function, true function value to what we actually observe is really important. And so this is specified by the likelihood. So let's look at that in a bit more detail. Right. So here I've got kind of like a 1D example with 3 different made-up synthetic data sets. And I just called them like case count, like for example, how many admissions do you have in a hospital emergency room in each hour? Or rainfall, like what's the rainfall at some rainfall sensor over the course of a day? Or binary classification, is someone awake, yes or no? And so kind of like in the first case, our observations are discrete positive integers. In the second case, they're continuous and positive. In the third case, they're just discrete 0 or 1. There's clearly some noise, but there's also something common about all of these examples. What can you tell what's the commonality between the 3? True, but not what I meant. Some other thoughts?
Point data?
No, like the second one is definitely not point data.
Non-Gaussian distribution?
Yeah, and so this is all about kind of like the noise part of it. But the commonality that I had in mind is that there's still some signal, right? It's not completely arbitrarily like sampled class labels. It's not completely arbitrarily sampled positive integers. So you can still see that there's clearly like some, like here it's lower, and then it goes up, goes down again, goes up, goes down again. Here you've got some clusters of zeros here, and then some clusters of ones over here. And so even though there's some noise, there's still also some kind of signal in our observations, some correlations between data points. And so generally, what we want to do in modeling is we want to kind of tease out the signal from the noisy observations. We want to kind of find out, like, you know, like what's the bit that's not noise. And so we're kind of looking for some functional relationship that can describe our data, even if there's kind of like some extra noise that we cannot model on top of that, or that we cannot like predict. So we're looking for something that might allow us to kind of predict at new points, at new places, for example, like what might be the number of admissions in the next hour. So if we only had seen like this part, then we might say like, okay, like in the next hour, like what's the likely number of admissions, and it might still not be like, you can't exactly predict it's going to be 12, but you might be able to say like, okay, like if we look at this hour, the next hour is probably going to be between 8 and 14, and if instead we had looked at this data set, then you'd probably say, oh, it's going to be between like 3 and 6, kind of like being a bit hand-wavy. But so we're looking for like trying to learn what's this latent functional relationship that allows us to get some signal out of noisy data. And here the likelihoods that I've used are like a Poisson likelihood for the count data, a gamma likelihood for positive continuous data, and just a Bernoulli likelihood for binary labels. And actually the functional relationship was exactly the same for each of them. It's a made-up example. And then the only thing that was actually different about these 3 data sets was the likelihood that I've used. So the likelihood describes kind of like what's the distribution over observations given some latent function value f at xn. And then the correlations are captured, we can capture through the f of xn. So if you're really kind of generic about it, then we should kind of think of our likelihood as a distribution over all our observations jointly. So P of vector y given some vector of kind of latent function values for each observation. But in practice, we often make the assumption that our likelihood factorizes. So what does that mean? We're just basically making the assumption that the noise part of our observation is IID. So there's kind of like no correlations between the noise at one point and the noise at a different point, and all the correlations we can capture in the kind of signal part in the f of xn. And so if we have make this kind of factorizing assumption, then our distribution over all our hundreds, thousands of observations ends up just being a product of 1D likelihoods for each data point. And often this is like an approximation, like maybe in real life, in the actual data, there are some additional correlations in the noise, but this is one of those approximations that really makes it much simpler, like much more efficient to do the computation. So that's a common, almost always made assumption. I'm just pointing it out because I think it's good to be aware of like what assumptions and approximations are we making. Like they might not correspond to the real world. We might have to make them just so we can actually get some results out. But I think it's good to keep in mind this is like an assumption we're putting into our model. So now in the following, having made this factorizing assumption, I'm just going to look at the likelihood as for a single observation. So P of a single observation y given some latent function value at that point where we make our measurement. And this P of y given f, I think it's important to kind of like think about it like really it's a function of two arguments. So we can either think of mapping from some observation y to the likelihood P of y given f. So, or we can think of like given some f, what's the distribution over y at that value of f. So really, if we think of likelihoods, we should think of them as kind of these two-dimensional likelihood surfaces. And here I've shown you like some commonly used likelihoods. And you can see that they describe kind of different observation domains. So the y's can be unbounded or positive or bounded between 0 and 1, or even just be discrete values for Bernoulli and Poisson. Now, first, let's look at the Gaussian likelihood, because that's what like we usually cover when we talk about Gaussian processes. So here, we're looking at P of y given f for some fixed values of f, and then that's the distribution over what's the y. So in a sense, you can think of it if f was -2, so if the actual latent function value at some point was -2, then we have some distribution of kind of observing y that's centered at -2 and then has some kind of finite width that accounts for like the noise in the measurement. And that corresponds to kind of like a cut line through this two-dimensional likelihood surface. And we can also look at the cut line the other way. And the peculiar thing about the Gaussian likelihood is that it looks exactly the same. It's a symmetric surface, so it's kind of easy to confuse the two. So if you look at different likelihoods, then it's maybe easier to kind of like get a feel for what's the difference of looking at P of y given f for fixed f or fixed y. So on the top right, we look at P of y given f for different values of f. And then in that case, in that case, it's a distribution over the possible observation values y. So y can only be 0 or 1. And for a fixed value of f, we have a probability distribution. So here, the probability for y equals 0 and the probability for y equals 1 adds up to 1 in total because we have to observe something. And in contrast, if you look at the same thing for a fixed y, then it's not necessarily a distribution, it's just some function, and in this case, for example, you can see it does not integrate to 1, like the integral for p of y given f for y fixed to 1 is only 1/2. Similar for a beta distribution, so if we look at p of y given f as a kind of function of y for a fixed f on the top right, then all of these integrate to 1, and the f kind of just says like where's more of the mass, is the mass concentrated more at 0 or more at 1 or more in the middle, but in any case it's a valid probability distribution. And in contrast, if we have our observations fixed, then it's not a distribution. That's why it's kind of sometimes called likelihood of f for a given y and not kind of like a distribution. So that's the two views, and here's just kind of like a summary of all of them. So if f is fixed, then it's a distribution over y's. That's kind of like the form that you commonly see distributions in statistics textbooks. But then when we do inference, actually we are given our observation. We have a data set already, right? And we want to find what's an f that kind of could have plausibly generated the observations that we found. Then we look at our kind of 2D likelihood surface on the opposite axis, and then these are the kind of likelihoods of f for a given fixed y, and none of them are distributions. But still, they're kind of informative about like what's the f that would have led to the y. So now there's two important aspects of likelihoods that I want to bring up because they're really important to keep in mind when you want to actually work with non-Gaussian likelihood models. The first one is link functions, and the second one is log concavity. What's a link function? Well, we have to kind of match the latent functions that we want to model with Gaussian processes with the parameters of our kind of like likelihood distribution. So if you think of the kind of like generative model, so how would we model having generated our observations? We have some p of y given f, that's a distribution over values of y for some latent function value f. And f is kind of like defining the parameters of our observation model. So for example, in the binary classification, it would be the probability for class label 1 versus 0, and in some part of the input space, the probability might be large to get class 1, and in another space it might be low. But in any case, this probability parameter has a domain between 0 and 1, right? Like the Bernoulli parameter has to be between 0 and 1, whereas the Gaussian process that we use to model distributions over functions is unbounded. It could be between -infinity and +infinity. So a link function is basically a bijective mapping that brings the two together. Like in some sense, you can think of it as it takes the kind of like range of the GP with which we model functions. That's between minus and +infinity, and just squishes it to whichever range our likelihood needs for its parameter. So it could be between 0 and 1, or being a positive parameter. So, for example, for a Poisson likelihood, the parameter is the rate. So what's the average number of events per time interval? That has to be positive, because that doesn't make sense to think of like what's a negative number of events per time interval. And so we need to kind of like make sure. So here I kind of cheated when I showed these plots before. Like here I only looked at f being 0 to 10, and here f being between 0 and 1. But really we have to kind of like make sure that it's defined for all values of f, because that's all the GP can take on any values of f. And so that's why we have link functions, and then there's an added fun part for historical reasons. The link function is the one that kind of goes from the parameter of a distribution theta to something that you model with the function model f. So typically when we kind of build probabilistic models, actually what we're using is the inverse link function that takes the unbounded f and converts it into kind of a valid parameter for a probability distribution. Different likelihoods have kind of different canonical link functions or inverse link functions. So for example, for the Bernoulli distribution, it's common to use a logistic inverse link function. And then for Poisson, often people use an exponential link function. But for example, for Bernoulli, you could also use a probit, like basically taking the CDF of the standard normal as the link function, works the same way, but it's a different model. And likewise, for Poisson likelihood, you could use the exponential to turn something between minus infinity and plus infinity to a positive value, but you could also take a square or softmax. There's lots of different bijectors from plus minus infinity to the positive real line. Which one should you use? Well, it's a part of your modeling assumptions. So in a sense, it's something that you shouldn't just unquestioningly copy from the PhD student before you or the paper that you read last week, but it's something that can actually affect your results. So again, it's just something to keep in mind, like different link functions have basically incurred like different properties in your model. So if you want to use non-Gaussian likelihoods, you need a link function. Just keep in mind it's something that you have to kind of like check. Is it like a valid model, just as any other parts like your priors on your parameters? Right, and then that was link functions. And the second aspect is log concavity. So who of you knows what a concave function is? So like a small number of you, like a quarter of you. So a concave function is basically one that has negative curvature everywhere. So like I like to think of it as a kind of frowning smiley face function. So the formal definition of a concave function is that if you kind of like take any 2 points on your function and you connect them with a straight line, then that straight line is strictly below your function, like in this picture. And kind of taking this and applying it to likelihoods, then log concave likelihood is a likelihood for which the log likelihood is concave, if that makes sense. So here's, so here's basically the likelihoods we saw before, but now on the log probability or the log likelihood scale. So like for a given y, we look at log p of y given f as a function of f. And then you can see for the Gaussian, obviously the log of e to the minus x minus f squared is just minus x minus f squared. So that's a negative parabola. But even for other distributions such as Bernoulli or Poisson, the log likelihood is still a concave function. And there's one here for which that's not the case. So the student's t likelihood, which is kind of like one of the classic likelihoods for you want to model data with outliers. So if you want to do robust regression, it's common choice to use the student t likelihood. But that one is not log concave. And what does that mean in practice? Well, like lots of kind of algorithmic guarantees such as convergence depend on the likelihood being log concave. So if you use a student t likelihood, then you might need like some kind of bespoke implementations that manage the kind of lack of guarantees you get. So it's similar to how convex optimization is really straightforward and non-convex optimization is kind of infinitely harder. Yes?
Does it have something to do with the tau decay? Like the heaviness of the tau?
No, it's just about basically like whether, it's literally just like kind of like whether the tails of the likelihood, yeah, maybe you can think of it like that, but basically like if there's like, if the log likelihood is non-convex, so here, Yeah, so here basically if I connect those 2 points, then the line between this point and that point would be above the log likelihood. And so that's not concave, and then that just gives you kind of like implementation issues. I don't want to dwell on it too much. It's just basically like if you use student's t likelihood or some other likelihood that's not log concave, then you might want to check even more carefully, like is your method converging properly, or are you running into numerical issues? So back to GPs, like I mentioned before, like often we look at the sausage plot, but it's nicer to kind of think of the function samples, or think of the distribution over functions in terms of its samples directly. So first, let's think about kind of like the generative model. So let's say we want to do binary classification. Like how can we model that? So we start with a functional prior P of f. And then we said we want binary classification. So we need kind of probability, like a probability of class 1 across our input space. So we take our inverse link function, in this case the sigmoid, to squash the numbers are maybe a bit small, but like on the left here, this is like -3 to 3, and then the link function makes sure that it's 0 to 1. So this is just kind of like a bunch of different samples, but like if we want to sample one data set from our kind of generative model, then we have to pick a single sample of the function. So let's take this one. And after we got this kind of like sample of a probability function over our space, then for each observation point, we then can sample like class 0 versus 1 based on the probability. So where the probability is around 0.5, then we get both classes in even proportion. If the probability is very close to 1, then you basically only get class 1. If the probability is closer to 0, then you mostly get class 0. Now, that's the kind of generative model. What we actually care about is we've got some data sets. Like, what was the function that generated the data set we actually have? So now we want to kind of like find our posterior. What's like the distribution over functions that could have plausibly generated the data set we actually have in front of us? And like, if we can do that, then basically we get kind of like posterior distribution over functions, and we can also look at the posterior distribution in this kind of like parameter space of our likelihood. So here we're looking at the posterior over probabilities directly. And you can see where we had more ones, the probability, like the inferred probability is higher, and where we had more zeros, the inferred probability is lower. And of course, there's still some uncertainty because we only have finite data. If we, and this is, I think, the comparison with the green line is kind of like what I used originally to generate the data. So you can see that the posterior kind of matches quite well the actually generating function. If we don't like the uncertainty in our posterior, what can we do? We can collect more observations, and then our posterior contracts. And you can see still kind of nicely matches the true generating function. So I just showed you the posterior. Where's the problem? So the problem is that like I kind of cheated a bit. So it wasn't the true posterior. It was like using already approximate inference to get something that I can compute and then put on a screen. But let's look at like why is this intractable in the first place? So yeah, who's familiar with Bayesian inference? Yeah, most of you know, especially after the last day and a bit, right? So we have our likelihood P of y given f. We can form the joint distribution P of y and f, which is just the product of P of y given f, the likelihood, times P of f, the prior. And then we use Bayes' theorem to get the posterior. P of f given y is P of y given f times P of f divided by P of y. Right? So far, so simple. And now this is the posterior for the function values at our observations. And generally, we don't only care about kind of analysis of like what was the function value where we made observations. What we often care more about is like, you know, what happens at different sites where we haven't measured before, like what happens tomorrow or what happens in a place where it's hard to collect data. So we care about the predictions at new points. So in the first place, we can predict what's the latent function value, kind of like what's the signal at the new point x star. And then that's, of course, just taking the kind of GP conditional P of f star, given we want to know f star at x star, and we know at our observations vector x, we had the function values vector f, times the posterior at the kind of training data. And the posterior at the training data is, again, kind of like just Bayes' theorem here written out with the likelihood, and you'll notice I've made this factorizing assumption already. And so we can kind of summarize it as kind of like taking the denominator as this normalizing constant z. Who of you remembers what z is commonly called? Partition function, but that's more statistical physics. And then, yeah, and I'm sure someone must have mentioned it yesterday. I wasn't here yesterday. Model evidence, very good, or marginal likelihood. Yes, and the marginal likelihood is this kind of normalizing constant that makes sure our posterior is actually like a proper distribution. And especially like when I started out learning about kind of Bayesian modeling and working with GPs, I was like, this P of y, like that's kind of weird, right? Like y is given, what does that mean, probability of a data set? So like I think one thing that maybe is often just like left under the table is that this P of y isn't just like probability of some observation. It's like kind of the probability of some observation under, like given all the modeling assumptions that we are making. So in a sense, you can kind of think of this z, the marginal likelihood, it's like the P of y given all the modeling assumptions. So what are modeling assumptions? Let's see if you can come up with some. Yeah?
You're using a linear model?
Yeah, so like that you're using a linear model, like what other parts go in there? So yeah, what your likelihood is, whether you use a Gaussian likelihood or student's t likelihood or gamma likelihood, that's one of the modeling assumptions. What else? Yes, so the link function is one of those modeling assumptions. So like a different link function, different model, different marginal likelihood.
Observation noise?
Yeah, so like hyperparameters of the likelihood, like what's the observation noise. Also, like what kernel do you use for your Gaussian process? What hyperparameters do you use for your kernel? So all of these things are kind of modeling assumptions, and that I kind of summarized in this curly M. So if you feel confused by what's probability of my observation, my data set, just remember it's like probability of my data set given like a range of modeling assumptions. So yes, let's look at the posterior. So if we have a Gaussian process prior to model our kind of correlations between latent function values, then the prior at our finite set of observations is just a multivariate normal. If we have a Gaussian likelihood, as was discussed at length yesterday, then this is the so-called conjugate case, and then the posterior is also Gaussian, because we take a Gaussian prior here, and we multiply it with a Gaussian likelihood, and the product of two Gaussian distributions is another Gaussian distribution. Everything can be done in closed form. Beautiful. if we have a non-Gaussian likelihood, so any other likelihood, then the posterior P of f given y is also non-Gaussian and intractable. And just to show that in 1D, so here's 3 different likelihoods, Gaussian, student T, and Bernoulli. So first, I'm just showing you the prior, same prior in each case. And in this kind of like 1D example, it's just 1D Gaussian. Then here's a likelihood for different observations. So for Bernoulli, I have to use either class label 1 or 0. For Gaussian students here, I use something a bit further away from the mean, so you can kind of see the effect better. And then the unnormalized posterior is basically just multiplying prior and likelihood together. But now this is not yet actually a distribution, right? So we have to normalize it. And, sorry, yes. So, sorry, the purple one is just prior times likelihood, so you can see like it's less than the prior in this case, but then not a distribution, and then we can renormalize it to find the actual posterior. And so here you can see for the Gaussian likelihood, then the posterior is also a Gaussian distribution. For the student T likelihood, even though the likelihood itself doesn't actually look that different, kind of like especially on the screen in the distance, but you can see that the tail is a lot wider on the left side than on the right side. And then for the Bernoulli likelihood, obviously you can also see that the posterior is actually not Gaussian, it's like strongly skewed to the right. And because just 1D is a bit boring and we can't really talk about correlations between function values if we only have one function value, I'm going to move to 2D, which is kind of like the best we can properly visualize because then we run out of dimensions on the screen. So here we've got 2 binary observations at 2 different points. Now our prior is a 2D multivariate normal distribution with like a little bit of correlation, as you can see here. And for binary classification, you can kind of think of the likelihood as cutting out kind of like, how do you say, like kind of each observation kind of like cuts 1 dimension out of our prior. And so if we have 2, then it kind of takes a quarter of the space. If it was, in this case, it's like label 1 and 1. If it was 0 and 1, then it would be a different quarter that it would cut out. Here I've just overlaid the prior and the likelihood, and then if we multiply them together, we get our true posterior that's very much non-Gaussian, has this kind of slightly X-shaped thing. So where's the problem? I can just show you some plots of what's the posterior. But the crucial thing is like, so here I did the kind of renormalization numerically, and this is fine if you do it in 1 or 2 dimensions. But so if we have a posterior for just 1 observation, then there's just a single integral in the denominator. If we have 2, then now we have to integrate over 2 dimensions, and so on. If we have n observations, then the normalizing constant involves an n-dimensional integral, and integrals become exponentially hard in the number of dimensions. Like if you wanted to approximate it with like evaluations on a grid, and you have 2 grid points per dimension, which is really not very much, and you have 10 observations, that's already 1,000, order of 1,000 evaluations. If you have 100, then it's like already a lot more. So that's basically the bit that makes the whole non-Gaussian likelihood inference intractable. All right. So what we've covered so far in the first half is what's the likelihood P of y given f, like cases where it's non-Gaussian, and why the posterior becomes intractable. And I think this is a good moment for me to take a sip of water and for you to think if you have any questions.
Why can't you ignore the normalizing constant?
Why can't you just ignore the normalizing constant?
If you have a Gaussian inference, you do like posterior mean, you can ignore it.
If you don't know what the normalizing constant is, then you can't do anything, right? So like if you can evaluate what's the unnormalized posterior for some new point, right? But if you haven't normalized it, it's kind of meaningless. So if I tell you the unnormalized probability is 3, what does that mean, right? Like it means nothing. If the normalizing factor is 30, it means that the normalized probability is 0.1. If the normalizing factor happens to be 300, the probability is actually 0.01. So without the normalizing factor, like the unnormalized posterior doesn't tell you anything. You can't sample from it. You can't evaluate the probability of observation or anything like that. Right. Any other questions? All right. So let's see how much I managed to cover in terms of approximations. All right. So just to recap, we had our joint model of observations y and latent function values f, where we are modeling the correlations amongst the function values. So that's kind of describing the signal that we're trying to extract from the noisy observations, and we're modeling those with our Gaussian process prior here. Then we can get the posterior distribution at training points, P of f given y. We can find the posterior at new test points x star, P of f star given our set of observations y. And then the other thing we can look at, so that's also something that maybe makes more sense if you think okay, let me rephrase. So with the Gaussian likelihood also sometimes people get confused over whether they're predicting f star or y star. So if you think about the Bernoulli likelihood, it's very simple. If we think about predicting f star at some new test point, effectively you're asking what's the probability at some test point. If you're asking for P of y star, you're asking like, give me a sample, let it be class A or class B. So kind of like going back to the Gaussian case, you can also think of P of f star given y or P of y star given y. And P of f star given y is kind of like just the signal part. And P of y star given y would be like, what's the noisy observation? Like, what's our prediction for the noisy observation? So with the Gaussian likelihood, often you don't actually care about P of y star. But yeah, just maybe also something to keep in mind. So these are all the things we can formally do, regardless of whether it's Gaussian or non-Gaussian likelihood. But with the non-Gaussian likelihood, then most of these become analytically intractable. So we have to make some approximation. And commonly we call this approximation Q of f instead of P of f given y. So Q of f is the approximation to the true posterior P of f given y. And then I'm going to talk later about how do we get Q of f. But if you have some approximation to the true posterior Q of f, then you can just replace the P of f given y for the posterior prediction with the Q of f here. And then we can still integrate out the kind of latent f's at our observations. And then we end up with the Q of f star. So this is like the approximate posterior at the test point. And likewise, you can also get the approximate predictive distribution. So how can we approximate our distributions? Thoughts?
Laplace approximation.
Laplace, very good. Variational, yeah, you already know what I'm going to be talking about. Great. All right, MCMC, very good. Like you've covered the second half. I can go home now. Right, so different ways of approximating distributions. So kind of like before we get to actual implementations and methods, first we can kind of approximate our complex posterior with a single value. So that's, you can kind of think of it as a delta distribution or equivalently like a point estimate of the posterior. Doesn't tell us anything about uncertainty, so maybe not very interesting if you want to do like Bayesian or probabilistic modeling. We can improve on that by considering a mixture of delta distributions. So then that's what we do in MCMC, Markov chain Monte Carlo, but also if you work with neural networks and use like an ensemble of neural networks to kind of capture uncertainty in some sense, then you're also effectively using a mixture of delta distributions. Alternatively, we can approximate our true non-Gaussian posterior with a Gaussian. You might think like, that's a bit weird, is a bit weird, like works quite well in practice to a large extent. I'll be talking about that in the rest of the lecture. Both Laplace approximation and variational inference generally kind of like approximate the true posterior with some Gaussian. There's also other methods that I'm not going to go into much detail, such as expectation propagation, power EP, and so on. And also you could like get an even better approximation of a true posterior if we look at the mixture of Gaussians, but that becomes even more complex, and I'm not even going to mention that again. All right, so let's have a quick look at MCMC. So Lisa talked a little bit about it already. So Markov chain Monte Carlo involves two things. A Markov chain, what does that mean? It means that we have kind of like a set of states. So like state here is like a kind of a set of values for all the parameters in your model. So if we have a GP model, then it might be like the function values, latent function values at every observation. So there's like n latent function values, and then maybe the hyperparameters of the kernel and so on. And Markov chain just means that xt only depends on xt minus 1, and xt plus 1 only depends on xt, and there's no dependence kind of further back. So Markov chain means there's kind of like a one-step history for the samples x1 to xt. And so xt plus 1 is a distribution that only depends on xt, and it's independent of xt minus 1, xt minus 2, and so on. Now the Monte Carlo part just means we roll the dice and draw random numbers. And the idea of MCMC is we want basically a random number generator that gives us samples from the true posterior P of f given y. Because we can't evaluate the normalizing constant, we can't just like draw samples directly. Otherwise you could just like do very simple like rejection sampling or something, but we can't do that. Fortunately, it turns out there are ways of sampling from the true posterior that only require evaluating the unnormalized posterior. And here I've called it h of f, which is the likelihood times the prior. And in MCMC, what we need is a kind of Markov proposal. So what basically a distribution that suggests a new state given the state that we had so far. And obviously, we need somewhere to start. And then here, like one very simple implementation of MCMC is you just start at some point, then we have a random proposal, and commonly that depends on the previous state. So for example, if this was our initial state, now we have a proposal that's a symmetric distribution around the last state. Then we draw a sample from this proposal distribution, and then we just need to decide, do we accept or reject this proposal? And the acceptance probability is given by the h of kind of proposal divided by h of last state. And this is what basically ensures that we're actually sampling from the true posterior. If we accept, then our next state is going to be the proposal. And if you actually want to implement this from scratch, and a very important part is that if you reject, you still get a new state, but the new state happens to be a copy of the previous state. So reject doesn't just mean like try again. Reject means take the previous state, copy it, and that's the next state. And then you try again. And in cases where h of x prime, so the unnormalized posterior of the proposal, is larger than the h of the last state, so when basically in places where the proposal is kind of like closer to a mode of your true posterior, then this is always accepted. So that kind of gives you this climb uphill. But then by rejecting, by kind of having some probability of accepting moves, even if they go kind of downhill, this is kind of like what allows MCMC to actually spread and cover the full posterior. And I've got a demo in 2D. Demos are always tricky. Let's see if this one works out. All right. Okay, so here we've got our 2D binary classification with a little bit of correlation. And here I've shown you the true posterior, right? Like in 2D, I can just numerically compute the normalizing constant and plot it. In higher dimensions, I couldn't kind of do the comparison to the true thing. But that's where we start. Okay, all right. So we start with some initial state. Then we have some proposal distribution conditional on the last state. And then we draw a new proposal. So in this case, the proposal would be take the point over here. Then we decide do we accept or reject it. In this case, it got rejected. So we stay where we are, and we get a new proposal. And this time it gets accepted. Oop. Uh-oh. Yes. And then you get kind of like this history of states that we had before. And the one where we had a rejection, it kind of ends up being thicker because we have two states kind of on top of each other. And then the Markov chain wanders through space, eventually gets to where the posterior has more probability mass, gets up to the hill, but as you can see, we can still wander around. Like, it's not just like find the maximum. It's not just go to the mode and stay there. It actually explores the posterior. And then if you do this long enough, I'm not going to go through them all one by one, then you can see we now get a set of samples covering the space. And yeah. So then you already saw the trace plots in Lisa's talk. We can kind of look at, so here we've got those two parameters, right? Function value at first observation, function value at second observation. So we've got F1 and F2 as our two parameters. So they're like both here. And then you can look at lots of diagnostics and things like that I'm not going to go into detail. I'm going to point you to a place that's great if you want to learn about MCMC. But just so, as a kind of like important part, so the first samples that we generated, right, they're a terrible approximation of the posterior because even though it's like the Markov chain has like a one-step history, there's still kind of like some autocorrelation, as you can see here. So like at the beginning of our MCMC sampling, things are very influenced by what point did we choose as the very initial proposal. And so you can see like at the start, like this is not very representative of the true posterior. So that's what's often called like burn-in or warm-up phase. And some implementations automatically discard it for you and figure out how much to discard. But like that's an important part of MCMC. Like don't use the very first part of your chain, basically. Yeah. All right, let's move this back. Right. So just looking at kind of like a marginal of our 2D posterior. So we've basically ended up with a lot of samples. And then if we plot a histogram of the samples, you can see that this actually matches the true posterior quite well. Obviously, if we had more samples, then the histogram would be less noisy. Right, so important properties. Yeah, there's a burn-in phase. So acceptance ratio, basically if the acceptance ratio is too high, then if you always accept, it kind of means you're kind of just going up to the mode and you're not properly like exploring. You're kind of stuck in the mode, just like going uphill. If your acceptance ratio is too low, then you never explore either and you kind of are stuck at your initial state. So typically in MCMC, there's like some actual very interesting works on like what's the theoretically optimal acceptance ratio, and like it's kind of on the order of 60 to 70%. Like you don't want to accept too much and not too little. So that's something that like is important. Yeah, like you want, yes?
So when you ran the multi-binary distribution before,
That's what you should do. That's this kind of like burn-in phase that I mentioned, or warm-up phase. Yeah?
So my question is, do we need to diagnose the MCMC samples if we have large numbers of parameters, as we know the Gaussian process has?
Yes. Yeah. So this is like, so MCMC is great when it works, but like you have to like convince yourself that you're, like it's easy to like take a package and say like, give me some samples. But like whether these samples are actually representative of the true posterior is difficult if you don't know what the true posterior is, right? So then that's why there's all these different diagnostics. So here in this example, I only had kind of like a single chain, so like a single run of Markov chain. So typically you do like multiple chains in parallel, so with different initial conditions, and then you can see like, do our different chains actually agree with each other? Like then like, you have some stronger confidence that they all kind of properly explore space because they all agree with each other. If you have like one trace up here and one trace down here, then you know it's bad. Yes? Yeah, so there's like lots of things. I probably shouldn't delve into too much detail here because I'll run out of time for the rest. But yeah, so like basically MCMC is commonly seen as the gold standard because it can be very accurate if you use enough samples and if all your diagnostics criteria like check out. It then in turn can be relatively slow. Though if you only have like a couple hundred observations, then MCMC is still pretty fast. And if you want to learn more about MCMC, I highly recommend Michael Bettencourt's website, and you'll get the slides later as well, so you don't have to write it down. But Michael Bettencourt did an amazing job at basically covering everything about MCMC in detail with these super lots of visualizations, and it's all like notebooks that you could in principle run yourself. So yeah, just basically what I wanted to make sure is that you don't think, oh, MCMC is just a black box that can press a button and walk away. Like things can still go wrong. If you want to use MCMC, just here's some keywords that you should learn about and read up about. This is basically the same slides that Lisa had with pretty much the same logos. Any questions on MCMC? All right. Yeah, some short takeaway, look at Michael Bettencourt's website if you want to learn more. It's excellent. And otherwise, ask me over lunch, or I'm still around tomorrow. Okay, so that was with samples. Now, in the last part, I'm going to talk about how can we approximate the intractable non-Gaussian posterior with a Gaussian. And you already mentioned a couple of ways we could do that with Laplace approximation or with variational inference. Why would we want to approximate a non-Gaussian posterior with a Gaussian? Sounds like a terrible idea, doesn't it? Yeah?
It's a conjugate line.
Yeah, so one really nice thing about Gaussian approximations is that, I know I don't have a slide for this, but remember, if we want to predict at a new test point, maybe I can write on here. So we want P of F star. Can you read that from the back? Yeah. So we want P of F star given Y effectively, right? And then if we do the exact thing, it's P of F star given F, P of F given Y, integrating out the latent F's at the training data. And this is the thing that's intractable. So then we approximate the whole lot by still having our P of F star given F. That's still like a nice Gaussian conditional. And then we have our Q of F dF. And if our Q of F is MCMC, with lots and lots of samples to be very accurate, then basically for each of those samples, you have to do the GP conditional and then keep around all of that. Whereas if we use a Gaussian approximation, then we can do the whole thing here in closed form. And it's basically a lot more efficient if you want to do lots and lots of predictions. Yeah, sorry, I did actually have a slide for that. I forgot. All right, yes. So if we approximate our true posterior with a Gaussian, then we get a very efficient way of predicting at test points. Second demo attempt, let's see. Right. So here's exactly the toy example we just had, same sample. So here we've got our whole actual kind of input domain, and we had one observation at 0 of class 1, one observation at 1.2 of class 1, and you can see in the MCMC posterior, basically all the samples suggest that the probability close to our 2 observations should be also closer to 1. And then that's the posterior, just at the 2 observations. So if we approximate with Gaussian, oops, should have put this to 0. So you can see, like, now I'm approximating the posterior with the Gaussian. I can change the mean of the Gaussian. And if I kind of try and match the true posterior, let me see, what can I do to make it look a bit more like that? Then maybe I need a bit less variance. Then you can kind of make it look a bit similar. Can you see that? Right, so now the big question is just like, how can I automate that so I'm not like staring at it on the screen and varying the parameters of Q of F by hand? Okay. So the task is basically, what are the parameters of our approximating Gaussian distribution? And there's, like you already mentioned, Laplace approximation. That basically is like kind of like a local approximation, and variational inference and expectation propagation kind of are more global approximations. And I'm trying to get through both of those very quickly in the last 15 minutes. So let's start with Laplace approximation. So the idea is we have a true posterior. We don't know what the normalization constant is, but we can evaluate the unnormalized posterior. And if we look at the log probability of a Gaussian distribution, well, that's just a quadratic polynomial. And we can get a quadratic polynomial that kind of represents the true posterior through what's called a Taylor expansion. Who of you is familiar with Taylor expansion? All right, like 2/3 of you. So Taylor expansion is kind of like a polynomial expansion of a function. So we just say kind of like it's one way of finding a polynomial approximation to a function based on evaluating the function and its derivatives at a single point. So we can write kind of like the expansion of a function at a point, kind of like in a small region around that point, is the function value at the point plus a linear term that depends on the derivative, a quadratic term that depends on the second derivative, and you could do this to any order, but here we only need the first 2 because then we end up with a quadratic approximation to our unnormalized posterior, and then we can turn that back into a Gaussian. And practically, how we do that is we kind of find the mode. So where would we want to do this quadratic expansion, right? Like we don't want to just do that. Oops, I must have the window here. 1 second. There, that's better. So we could do this Taylor expansion anywhere, but like then it's probably a bad approximation. So we kind of start with a point estimate. We try and find the mode of the true posterior first. And then that's something that can actually be done quite efficiently through second order optimization methods like Newton's method. Caveat, doesn't work so well if you have a non-log concave likelihood. So like Laplace approximation with a student t likelihood is basically like its own set of research papers. But if you have a log concave likelihood, like most of them are, then it's very efficient to find the mode of the true posterior. And then we basically match the curvature of the true posterior with our kind of approximate Gaussian. How does that look like in practice? So here we've got the prior in blue, the likelihood in red, the unnormalized posterior in purple, because it's blue times red, and then the thing that we would like to get that we can't actually do analytically in high dimensions, the true posterior in the dashed green line. So we do the expansion in log space because that's where the Gaussian is a parabola. So now the prior in blue is just a quadratic function, and otherwise it's the same as before. So here I'm looking at the unnormalized posterior in the solid line. That's the thing that we can evaluate. And then in log space, the normalizing constant is basically just a constant shift. That's the bit that we cannot actually compute in closed form. So let's throw it away. Now all we have is the log, like the log of the unnormalized posterior. So basically like log of prior plus log of likelihood. And Newton's method is, let's start somewhere, doesn't really matter where, then do a quadratic approximation at your first point, then find the maximum, and then evaluate at the maximum. That gets us down here, and that's our second point. And then we can do another quadratic approximation around the second point, find its maximum, then evaluate what's the unnormalized log posterior at that point, and you very quickly jump to the mode, and then that's where we take the quadratic approximation. So here we've got the kind of first and second order Taylor approximation. And then we can just undo the kind of log space move and take the exponential of what we had. And the exponential of quadratic just happens to be a Gaussian distribution. And the key thing is, because it's a Gaussian distribution, we can analytically compute the normalization constant. So then that's what allows us to immediately say, like, okay, now we have a valid probability distribution. And this is how it compares to the true posterior. So same thing in 2D. Now our approximate distribution is like a 2D Gaussian. And so you can kind of see how it's moving to the mode and then kind of like quite closely matching the posterior at the mode. So one thing about Laplace is that because it only sees the local curvature around the mode, it isn't really able to kind of represent the bulk of the distribution. And you can see that the peak of the Laplace approximation is actually, like even in this simple 2D example, like visibly different from the true mode of the unnormalized posterior. The true mode of the posterior, the mode of the true posterior. And this is kind of like a property of Laplace approximation in general. So especially with binary classification, Laplace approximation gives you a relatively bad approximation that's kind of not well calibrated. And we can kind of think of it as a point estimate plus plus, so like point estimate with added uncertainty. It's very simple. You can actually implement it in like 10 lines of code. It's very, very fast. If you look at the Gaussian processes for machine learning book, there's like some neat ways how you can exploit that the GP prior is a Gaussian itself to make it even more efficient. But it's a poor approximation if the mode is not representative, such as with classification. And like I mentioned, for non-log concave likelihoods, it doesn't necessarily converge. So another way of getting a Gaussian approximation is to kind of look at the global property. And here I'm going to focus on variational inference. Sometimes it's also called variational Bayes. I don't know why. Maybe one of you knows, like, tell me later, like, why it's sometimes called one or the other. But what's the big picture? So variational inference is a kind of a recipe for finding an approximation to some intractable distribution. And so here I've kind of visualized the intractable distribution like that we're looking for, like the true posterior is living in some space of probability distributions. And now what we need is like some kind of like smaller space that has nice distributions in it, distributions that we know how to deal with, that we can parameterize. And for that we'll use a multivariate normal Gaussian distribution. And then what we need for variational inference is some way of computing distances between distributions. Sorry, not between, yes. Computing a distance between like an intractable distribution P, like our true posterior, and a tractable distribution Q from like some smaller space of like nice distributions. So our like intractable posterior could be like some multimodal thing like this, and then like approximate distribution could be a simple Gaussian like the blue one. And then here we've got two different approximations, and we want some way of saying like the red one is closer to the true posterior than the blue one. So then all that variational inference does is basically find a distribution Q out of this kind of simpler space of distributions such that it minimizes the distance to the true posterior. So just that. And then we use this Q star, that's kind of the closest of all the distributions in our nice space of multivariate Gaussians, and then we use that as an approximation to the intractable true posterior. How can we measure, like how can we find the distance between distributions? There's lots of ways, like you can use Wasserstein distance and all kinds of things, but here we're just going to look at what's called Kullback-Leibler divergence. Who's familiar with that already? Yeah, about half. So Kullback-Leibler divergence is not really a distance because it's not symmetric. It's also referred to as like the relative entropy, or like there's like a bunch of different ways you can kind of like think of it, but it's effectively defined as this integral, or equivalently like an expectation under Q of the kind of log Q of f divided by P of f. And like, no worries if like this is not essential for using VI, but like helpful if you want to understand the derivation. So like 3 important properties of the Kullback-Leibler divergence are: it's non-symmetric, it's always positive. Like this is something that's can be proven in what's called Gibbs's inequality. It's maybe a bit surprising because the log here, like Q of f could be larger than P of f or smaller, so the log could be positive or negative. Why would the expectation of something that can be positive or negative be strictly positive? That's an interesting proof. And the KL divergence has, at its minimum, when it's 0, that means that Q and P have to be exactly the same distribution. So that's the 3 important properties. And then in variational inference, we're basically finding the Q of f that we choose to be commonly, for example, with GP is a multivariate Gaussian distribution. You could, in principle, use other distributions here as well. But multivariate Gaussians are easy to parameterize. We know how to handle them. And then we just minimize the KL from the true posterior to the approximate posterior. Simple, right? All we need to do. What's the, yeah?
So if using variational inference using the, so you just basically minimize the KL divergence.
Yeah.
What about the loss function components? I mean, usually, like in neural networks, we like compare the labels and then add that KL divergence component.
Okay, I'll get there. I think you'll see that on the in the next 5 minutes. Yeah, right. So all we are doing is we're minimizing the KL divergence from the true posterior to the approximate posterior. Where's the challenge in this? yeah, we don't actually know the true posterior. How do we evaluate the KL divergence from something that we don't know? That's the key question. So we want to minimize this KL divergence. All right, so here's going to be a little bit of maths. Hopefully I'm going to manage to go through it slow enough that you're going to follow along. Otherwise, look at the slides in your own time again later. But yeah, so first I'm just taking this KL divergence and actually write out what's the definition of the KL divergence. So here we've got our integral over the approximate posterior times the log of the fraction of approximate and true posterior. And I've highlighted the intractable quantities in red so that they're easy to spot. Then I can turn the log of a fraction into a difference of logs. So now instead of a fraction, we just have log q of f minus log posterior. And then now I'm using Bayes' theorem to turn the posterior into a sum of prior likelihood and marginal likelihood with appropriate signs. So far, so good. Now I'm combining the first two terms, which is the approximate posterior and then the original prior, and pull them together again. Does this remind you of anything? Yeah, so this is a different KL divergence. So before we had the KL divergence between true posterior and approximate posterior. Now it's prior and approximate posterior. So now this is something that's tractable because the prior is Gaussian and the approximate posterior is also Gaussian. What about the other terms that are left? Well, there's this term here that I'm going to convince you in 2 minutes that it's tractable. And then there's this term here that's the log marginal likelihood. Well, that's still intractable. Okay, what can we do about that? Let's see. So let's put the log marginal likelihood on the opposite side. Now here we've got, all I've did is reshuffle the terms, so I've moved this to the other side. And now I have the KL here on the right-hand side. Remember one of the important properties of the KL divergence? This term is always positive. So we can just throw it away. And then we end up with a lower bound to the marginal likelihood. So all I did was rearrange the equation, have the log marginal likelihood on one side, the KL on the other side, and now I'm using the property that it's always positive to get a lower bound on the marginal likelihood. So now we've got something that's slightly different. Log p of y is a constant with respect, log p of y is not a constant with respect to like model assumptions like what's your kernel or something like that, but it is a constant with respect to the parameters of the approximate posterior that we're trying to optimize. And this L of Q that depends on our parameters of our approximate posterior, that one does not depend on the intractable true posterior anymore. Now, this L of Q is strictly smaller than the marginal likelihood. It's a lower bound. And so maximizing the lower bound is equivalent to minimizing the true, kind of like the original KL divergence that we wanted to minimize. So those two optimization tasks are equivalent to each other. So instead of minimizing something that we cannot evaluate, now we are maximizing something that we can evaluate. And so we can fit our variational approximation Q by optimizing this L. And this L is often referred to as elbow, which stands for evidence lower bound. I'm sure someone thought they were very funny. I should have added an elbow emoji maybe for next time. And this elbow has two terms. So it has the data fit term. That's basically like the expectation of the log likelihood. And the regularization term that I think you might have asked about earlier. So that's where they come from. And now we've got an approximation to our intractable true posterior based on this Gaussian. And by defining lambda as the parameters of this approximate posterior distribution, we get L of some parameters, and then we can optimize that using gradient-based methods. I'm aware I'm about a minute or so past time. So can I go over by 5 minutes? All right. So yes. So one thing I wanted to point out is, like I told you, this is tractable. Why is this likelihood or data fit term tractable? Well, if it's a factorizing likelihood, then the log likelihood just turns into a sum of 1D terms, and then it's 1D integrals. And depending on the likelihood, these 1D integrals might either be analytically solvable, or if they're not analytically solvable, then 1D integrals is something that's actually super easy to do numerically. Like we've talked about how integration is hard in high dimensions, but if it's only one dimension, then integrating numerically is very accurate and very efficient. And if that doesn't work, you can always resort to more Monte Carlo and evaluate this term stochastically. So this is true for factorizing likelihoods. If for some reason you have a non-factorizing likelihood, then this might be a lot harder. And you can ask me in the break over lunch or something about my experiences with that if you want. But for factorizing likelihoods, we can practically optimize the lower bound, the elbow, and then get an approximation to the true posterior. So here's like the kind of toy 1D example we had before. If we start with our kind of initialization as Q of f being a standard normal, then we can do gradient descent on that. And here I'm showing you the exact posterior in green, then our kind of current state of approximation in red. And then here in the middle, we're comparing the true marginal likelihood in cyan, then the elbow in purple, and the kind of true KL in blue. And then here you can see kind of like what it looks like as a function of the parameters. So we're kind of slowly maximizing the elbow, minimizing the true KL divergence. Note that we can't actually compute this like in higher dimensions. All we can do is the elbow. But even in high dimensions, the elbow is still a lower bound. So you're bound to converge as you keep optimizing, which is a nice property of variational inference. And then eventually we end up at the parameters of our approximating posterior that give the kind of best approximation in some sense. So to summarize, like VI is nice because we're kind of directly minimizing some distance from the true posterior. One important property is that it's mode seeking. What does mode seeking mean? So if our true posterior has multiple modes, and our approximating posterior only has one mode because it's a simple Gaussian, then the approximating posterior is going to kind of like jump to one mode, and it might depend on like what initialization. Well, does it? Does it depend on the initialization? Might do. Depends on how you optimize. If you do proper global optimization, it's going to find the highest peak of your true posterior, but if you do like gradient-based optimization, see there's like always like implementation details in everything, regardless of theoretical guarantees. But at least in principle, like with variational inference, you can kind of check like does the optimization converge to something, so you'll get some answer, even for like not so nice problems. One key fact about variational inference that's very well known is also related to the mode-seeking behavior is that it underestimates the variance. So like, in a sense, that's kind of quite bad about VI. Like, you might end up with an approximate posterior that doesn't tell you how uncertain you really are. So that's something to keep in mind. There's another way you can do that's called expectation propagation. Last time I gave this lecture, I talked about it in more depth. I already cut it down last night, like for this time, and now I'm going to skip it completely. So just on this slide, I wanted to show you like same 2D toy example, just the comparison of true posterior dashed line. MCMC gives you samples, which are very good approximation to the true posterior. Laplace is fast, but kind of like you can see it's quite biased, and VI and EP in this case both give you kind of decent results, but you can kind of see that VI is kind of narrower than the expectation propagation. So, yeah. So I talked about these 4 different ways of approximating. So MCMC is kind of like gold standard but slow. Laplace is simple and fast, but often like very poor approximation. Even if Bayesian neural network people tend to quite like it these days. Variational inference is kind of principled, works very well for any likelihood. You don't have to worry about like log concavity of the likelihood as much as with Laplace, but it underestimates the variance. And I haven't really talked about expectation propagation. Lots of things we didn't cover. I'm going to skip that as well. And I'm just going to leave you with the main takeaways of this lecture. So first one is, if you don't just stick to Gaussian likelihoods, you can build much richer models that might fit your data better, where you can incorporate additional knowledge you have about your domain. Maybe Magnus might talk a bit about that this afternoon, I don't know. But like for example, in like genetics, like gene expression count, you know that you have counts, you know something about how your kind of like sequencing process throws away some of your gene expression counts, and you can model all of that and then actually build much richer models that much better represent the underlying process and then give you a better fit to your data. With non-Gaussian likelihoods, we can still learn latent functions that kind of form the correlations between our observations that give us kind of like signal from our noisy observations. If you have non-Gaussian likelihoods, then the true posterior is intractable, so you have to resort to one of many different approximations. They each have their pros and cons. They all have sharp edges and hidden pitfalls and implementation details. And hopefully I've given you some pointers for where to find out a bit more about each of those. And importantly, like we have trade-offs between speed, accuracy, and how easy to use they are. And then in the slides, you'll find some more references as well.
Fantastic. Thank you.